you hear me now? Hello. Test. Can people on Zoom hear me? Hello. Okay. I can be heard. God. All right. Good afternoon. How's everyone doing? Yay, that's less enthusiastic. All right. What do we got? Seems like we have a lab that's due this Friday. We'll be doing kind of a project one review. After that, homework two is going to be due next Friday, as well as lab six. We'll be covering kind of the important aspects of homework two today. Uh, Homework two is all about using this new data structure called a disjoint set. And we'll kind of be discussing how the disjoint set works for today's lecture. Now, before we get started, do we have any questions? Start off. Is this low resolution? Yeah. I don't know. It's the same thing as normal.
Oh,
I
yeah.
think it's just out of focus.
Oh, yeah, that again. Huh.
Yeah. I don't think they fixed the focus period. Oh, well. I can't fix the focus. All right.
One thing did you switch to HDMI one time? Did it work better?
No, I am on HDMI.
Well, you're on the VGA cable, though.
version of, I don't think it helped.
Well, where's the other cable? Just to try it. Yeah, this one. Plug in directly. Let's see. I'm gonna pray. It's only 30 seconds. I think you're right, but
That better? Is that better? All right. Either way, let's get started now. All right. So we've kind of finished our first phase of the class. The first phase of the class was going over Java and then asymptotic analysis, kind of getting us into the mindset of what we can do. All right. We figured out the syntax stuff. We figured out how we can analyze functions and programmatic methods. So now we're going to actually start going into the meat of our course, data structures. So over the next few weeks, we'll be deriving a bunch of new data structures. This part of the course is a lot slower than the first part. First part, we're just rushing through a ton of content. Now we'll kind of transition to this scheme where every 2 or 3 lectures, we switch to an entirely new data structure. So that does mean that it is somewhat fast-paced, but it also means that if you fall behind a few weeks, you can still come to lecture. Chances are we'll move on to the next topic, and you'll have a chance to kind of like build up from there as well, and then kind of look back at a previous topic later. So we'll be largely resetting every few lectures from now on. So today we're going to be discussing the disjoint sets data structure. And what we'll do first is we'll first introduce the problem that we want to solve, and then we'll kind of create bad versions of this data structure until we get to one that's reasonably good. All right. So the problem that we're trying to solve is we have some items. They could be, for example, countries. And our goal is to run these 2 operations. A connect operation connects 2 things. So for example, here I'm connecting Russia and China because they share a border. Here I'm connecting Russia and Mongolia because they share a border. And I want to ask, is connected, if it's possible to connect, to go from one to another using just these connections. So in this example here, China and Mongolia are considered connected because China is connected to Russia and Russia is connected to Mongolia. So in this case, is connected is going to return true. If I connect the US and Canada because they share a border, right now, the US and Mongolia are not connected together because there's a big ocean in the middle of them. But if, for example, I decide to add a crossing between Russia and the US, somewhere in the Aleutian Islands for some reason, Then all of a sudden, it becomes possible to go from US to Mongolia using only these edges. So we'll now call this true. Now, their practical uses we'll be kind of looking at throughout the homeworks. Homework 2 is about percolation theory, which is one particular use for a disjoint set. It does get used in other algorithms. Kruskal's is a big one that we'll be discussing later once we get to our graphs component, and it'll be using disjoint set as a subpart. So in order to simplify things, we're going to rely on this basic version of a disjoint set. For one thing, we'll all ensure that all items are numbers. So all of these sets are going to be just numbered 0, 1, 2, 3, 4, 5, 6. Here's an example of a disjoint set that contains 7 items at the start. And we'll start off with a set of items predefined. So we need to say how many items we have at the start of our disjoint sets. And we're going to start with everything disconnected. So when we create a new disjoint set of size 7, we're going to start off with this entirely empty board containing no connections. If we then connect 0, 1, we'll get this connection here, connecting the 0 and the 1 together with a line. Then if we connect 1 and 2, we'll connect these two with a line. If we connect 0 and 4, we'll get a connection here. 3 and 5 will connect this way. 2 and 4, we can check if they're connected. What is it? Is it true or false? True. Yes, because you can go 2, 1, 0, 4. So it is true. How about 3, 0? False, because you can't get from 3 to 0 using only edges. 4, 2, we can connect. 4, 6, we can connect. And if we connect 3, 6, what about now? Is 3, 0 connected? Yeah, from 3 to 6 to 4 to 0. Our goal is to design some underlying data structures that will actually make this work properly, right? We want to have these two operations, the connect and isConnected operation. And as a user of this, we don't particularly care how it works under the hood. We just want it to be fast. If you're driving a car, you don't care how the car's engine works, whether it's a gas engine or electric engine. You just care that the car can drive you somewhere. We don't really need to worry about the physics behind things. So this is kind of what we're doing here. Right now, we're going to be designing the car. Later, once you go into homework, you just need to know how to drive the car. And to drive the car, you just need to know it connects and it checks is connected. So let's take a brief look and see how we might be able to solve this problem. One naive approach we could do is just connect two things somehow internally, like record every line in some data structure and then check connectedness over all of this. If we want to check if two things are connected, maybe do some iteration over the lines. I'm not entirely sure how we're going to do this, but it seems like it's possible to code this up somehow. Is this efficient? No? Why do you say it's not efficient? Yeah, we might have a lot of calls. We might have a lot of items. We have to go through everything, right? In order to check if 4 is connected to 1, we have to go through 2 lines. We can imagine that there's the only path that's like 500,000 lines to get to a new place. It doesn't seem very fast. Is there any better approach we could do? Yeah? We can use a dictionary. We can use a dictionary to see what it's connected to. Yeah, that could still work, but still we need to go from 4 to 0 to 1 in this case here. So that's still not as efficient as we'd like. Yeah. Created a set for each of the connecting elements, and then you check to see what which set the different one is in, and see if the that's an interesting idea here. If you look at this carefully, we don't actually care how these are connected together. We just know that they are connected. So we can kind of treat this like left side as just the set 0, 1, 2, 4. All of these 4 items are connected to each other. We don't care how they're connected to each other. We just know that if you pick any 2 within that, it is connected. So we can kind of like create sets like this. We start off with everything in its own unique set. And each time we connect, we kind of merge together 2 sets. So when we connect 0 and 1, we put 0 and 1 together in the same set, because now you can go between the 2. 1 and 2 connect to make this. 0 and 4 connect to make this set, because now any items in this set, you can go between the 2 using just edges. If we connect 3 and 5, Now, if we check if 2 and 4 are connected, we just need to make sure if they're in the same set. In this case, yeah, they are in the same set. 3 and 0, are they in the same set? No. So you can't make it from one to another. We can then connect 4 and 2. Does that affect anything? No, 4 and 2 are already in the same set. We don't actually do anything in response there. Let me finish this slide first. Yeah. If we connect 4 and 6, then we merge those two sets together. If we connect 3 and 6, then we merge everything together into a single big set. And now every time we can check is connected, we are going to end up with a true. You had a comment?
Yeah, so for this, how do we, like, do we have some other data structure to tell us which set every element is in? Like, for example, if we're connecting, like, 3 with 6, for us to know that 6 is in a particular set, do we have some data structure that tells us that or?
Good question. How do we actually accomplish this in reality? Yeah, we're going to get into that and like show how we develop that next. Yeah. So if we just do this naively, then what we do is we just create some list of these sets. And in order to connect, we find the set corresponding to the first item, find the set corresponding to the second item, merge them together if they're different. To check if there is connected, we find the set with first item, find the set with second item, and check if those two are the same set. Is this efficient? Any problems you can think of about this approach? Yeah. What's the lookup time of a set? Yeah, we'll say it's constant for now. We'll show why that's true in lecture 19. Effectively, you can check any particular set to see if it contains an item. And you can add an item to a set in constant time. You can remove an item in constant time. Yeah. Yeah.
So assume you have like m different sets to search for specific, to search for which set of elements in the overlap.
Yeah. If you have, for example, 3 sets, you might not find the 6 until you check all 3 of these sets. We have to look in the first set to see if it contains a 6, then the second set if it contains a 6, then the third set if it contains a 6. In particular, like, it's really slow to like look at each of these. Yeah. So it is a nice idea to try this out at the first approach, but it is kind of really slow. Yeah. If you look at this, right? In this example, if you just start off with nothing connected, if you want to check is connected 5, 6, we need to look for the 5. That takes a long time to do because we got to look in each of these sets one at a time. Then we got to look into 6 and it'll take a while to find that as well. So our overall runtime is theta n in worst case. Yeah. Fair enough. Yeah. So this is too slow. We don't like theta n in this. We can do better than this. But the main point here is that just because we picked the structure, it is not going to work quickly. The list of sets version of this data structure is too slow. And it's because we fundamentally chose a wrong implementation under the hood. Let's take a look at another approach. Is there any other ideas we might have on how to do this? Yeah.
You could have like either an array or a map. Or that just like a given some element, the index of whatever set it corresponds to, and then you would just update that array or map or whatever in your connect.
Yeah, that's a good idea. We say here that maps can exist in a constant time access. And we can kind of use a map to show where each item is or which list each item is. In this case, we use an array here to kind of say, okay, I'm saying that the 0, I'm going to call this leftmost array 4 for some reason. I'm going to call this middle array 5. I'm going to call this third array 6. And the idea is everything in this array, 0, 1, 2, and 4, they're all in array 4. The 3 and the 5, they're all in array, or in the set 5. And the 6 is in the set 6. And as it turns out, if we do this, we don't even need the sets. We just need to check the numbers to see if they match. So in order to check if two things is connected in this case, all we need to do is check if two things have the same number. In order to connect two items, we need to replace values with their new number. So here's kind of the pseudocode for this. We create an array. When we initially create the array, we set everything to equal like some separate set value. And then if they're connected, then we just check if they're the same value. If we're trying to connect two sets, then we got to kind of replace all the values of one with the values of another to kind of merge them together. It doesn't really matter what the numbers are associated with each set. They just need to be different for each different set. So just as a quick check, how fast is this runtime? How fast does it take to check if two things are connected in this version of the data structure? Constant? How many people say it's constant? Theta 1. Yeah. Why? Yeah, you just check two spots, and if they're the same, then you're correct. How about connect? What's the worst case runtime for a connect operation? Yeah. Oh, then why? Yeah, if you have two separate sets, then you have to iterate through one of those sets to replace all the items. And that takes a lot of time. Even if you had a way to like find all the items at once, imagine that you have 500,000 items in set 0, 500,000 items in set 1. To merge them together, you need to do at least 500,000 operations. And that's really slow. So it's overall better in a way, but it's too slow for practical use. It's going to be taking way too long to connect two items. So we're not going to like this version too much. I'm going to suggest a version that's different. It's going to be kind of confusing at first, but we'll kind of show how it actually improves things. It's very difficult to come up with this on your own. Here's an interesting idea. What if, instead of just setting this up as like numbers, we're going to actually use a slightly different format for our sets. In this case, our sets represented the items of the same number. Instead, we're going to kind of represent sets as a tree. All right. So this is kind of an interesting idea. In this approach here, we create this kind of tree structure. And all we need to do is we say that each item has a parent. And that parent keeps going up this list. All items in the same set end up sharing parents or roots eventually. Why does this help as a question first? Yeah.
Assuming that for any given item, we believe we can figure out what its parent is in constant runtime. If that's an assumption we make, then to see if the two items are connected, we just have to see if they have the same parent. Or even if it's not an assumption, we can get the parent in constant runtime, you can still traverse the tree to find if they have a common parent fairly quickly.
Yeah, let's take a look at exactly that. In order to check if two things are connected, we just need to find the parents. And we're currently assuming that checking to find the parent, or actually the root, not the parent fully, because it could be the parent of the parent of the parent of the parent, etc. But finding the root of the tree, as long as that's fast, we can check if two things are connected really quickly. All we need to do is kind of traverse up this tree until we get to the root and see if the root is the same item. Here's another point that makes this fast. How do we actually connect things in this? We want to make it so that connection does exactly one operation. So how do we do that in this case? Yeah. Yeah, we can connect the 3 to, or what do you want to connect? Yeah. Yeah, we are making a tree overall. And I think the idea is there. We take this 3 here, the parent of the 5, and we kind of connect it into this tree somehow. Where do you want to connect it to? What do you think is the best place to connect this 3 node onto? Yeah, the 4? Why the 4? Not really. We just kind of need to make sure that items in the same set share the same root. It doesn't really matter which ones are connected to which ones too much.
Would you connect it under the 0 so that way it's really quick to find the root?
Yeah, I think I'd like to connect it to the 0. In order to do that, what do we need to change in our backing array? Someone in the back that hasn't talked? All right, I guess behind you.
We start with the 5 index, that consists of 3, and there's a 3, and then connect that to the 0.
Yeah. And intuitively, what this array does is all it is, it's saying what your parent is. So the 2 is a child of 1 because the value of 2 here is 1. The 5 goes to 3. The 3 goes to nothing because -1 we're using to denote a root. 2 goes to 1. 1 goes to 0. So what we do is we look at, when we're trying to connect 5 and 2, we go from 5 up to 3 to see its root. We go 2, 1, 0 to here. And now we just connect the 3 to 0. The way we do that is we just replace this 3 with a 0. So now this kind of array structure looks like this internally. Our mental model of what's going on is now this. So if we wanted to just connect 2 items, that's kind of all we need to do. We go up to the root of 5 to get 3. We go up the root of 2 to get 0, and we connect the 2 together. Does this correctly connect 2 sets together? Yes? No? All right. Does this make it so that we can check if 2 things are connected easily? Yeah. How do we check if 2 things are actually connected? Let's take a minute or so to discuss.
I don't know. Yeah, okay. I feel like people are following. I forgot where I put my thing. Right. I think maybe I need them sitting at the same time. I like understanding these questions. Yeah, I was going to leave them for a lot of time, but I found them. Right. It's better to be ahead of pace. As long as yeah.
All right. All right. Let's bring everyone back. All right. So how do you check if 5 and 2 are connected? And keep in mind that when you're doing this, you don't have anything below the array. The only thing you see is this array, because that's the only thing we're actually storing internally in our code. So how does your code determine if 5 and 2 are connected? Let's pick someone in the back because there's a bunch of people in the front who've been talking. Yeah.
That goes to the index of say value 5 and keep until you're just -1. Remember that index is same thing from 2 and 6 the index of
Yeah, that sounds like a good approach. So you start off by looking at the root of 5. And to get the root of 5, we start by looking at the index 5 here. We see a 3.
That's new. That's cool.
Hello?
Yeah, nice. This is the microphone then. Reboot.
Hello? I've done that a few times. All right. Test, test. Okay, hopefully there's no more, never mind, there's more clicking.
You have a phone in your pocket?
Yeah, I do have a phone in my pocket.
That's why the phone.
I would, oh! No, wait.
No. Ah, okay. So I thought it was.
All right, there's another microphone here. Right.
Definitely turning off.
All right, I'm gonna try continuing to use this mic for now. Maybe, okay, never mind.
Is it definitely the mic and not the laptop?
I don't know. I'm gonna try swapping to this one. It's good. Test, test. Okay, this one is not clicking. All right. Where were we? All right. So yeah, you take the root of 5, and the way you do that is you look at index 5, and that says my parent is 3. You go to index 3, and it says my parent is 0. You go to index 0, and it says I don't have a parent. I am a root. So therefore, the root of 5 is 0. Then we look at 2. What does 2 say? 2's parent is 1. So we look at 1. 1's parent is 0. 0's parent is nothing. 0's root is nothing because it is the root of its set. It's kind of the boss of its set. So because of that, 5 and 2 share the same boss, the root, same root. So therefore, they must be connected together. So that's kind of the main way of how we can check if they're connected. Now, let me ask, what do you think the worst case height of such a tree is going to be? If we just try to do connects like this, and we pick the root kind of arbitrarily, we don't look at how we're going to pick the root specifically when we connect two things. What do you think the worst case height is of such a tree? Feel free to discuss for like a minute or so.
This might run a copper.
Battery pack, right?
I think it died completely. I have no idea.
That works out?
But it's just like I run the cupping in a way that's like I'm an audio nerd. I don't even care.
I guess that's one way to get back on get back behind the base. All right. Let's bring everyone back. All right. How many people say it's theta 1? No matter what, the worst case height of a tree is going to be bounded by a constant. How about log n? The worst case height of a tree is going to be bounded by log n. Theta n? N squared? All right. It seems like a lot of people said theta n. How can that possibly happen? How can you get a tree that's theta n tall? Behind you.
We stack trees on top of each other, so it's basically the length of the tree size to the size of all the nodes.
Yeah, imagine that we do, I don't know, connect 4 and 3, then connect 3 and 2, then connect 2 and 1, then connect 1 and 0, and we end up this really, really long tree where every item is just the parent of its next child and so on. If we have, let's say, 100 items, we can make a tree that's 100 items long like this. If we had this, what would be the worst case runtimes for these operations? Theta n, why? Yeah. Yeah, we have to go all the way up to find the root. For both connected is connected, you need to do that at least once for both P and Q. So that's going to take a lot of time. Yeah.
Can't you just assume that as long as whatever's in the index isn't -1, then like you have to keep on going?
As long as the item you have in the index.
Like you go back there like if you say that check 5, and only 5 has 3 in the index, if you go to that index, you go for the zeros index, and you see that that has -1. But in general, you could assume that as long as it's not a -1, then there is a sense of negative.
There is a what?
They are connected.
As long as you don't have a -1, they're connected. I'm not sure I agree with you on this. Imagine if we come back to here, for example, 5 and 2 are not connected right now. Because if you go from 5 to 3, then you get 3 here, which is the root. Whereas if you go from 2 to 1, 0, -1, you end up at different roots. So it's not necessarily true that just because these two have a positive value, that they're going to be in the same root. Yeah. Good question. So yeah, connect and is connected. They're both going to take theta n time in the worst case, because if you imagine you're trying to check if is connected 4 and 4, then you got to go from 4 to 3 to 2 to 1 to 0. It takes forever to get up that tree. So this is kind of how we show this code. This find operation is kind of the root finding operation. Determine the root of the item. And then connection, we find the two roots of the items, and then we just set one to be the parent of the other. And then is connected, we just check to see if the roots are the same. Unfortunately, this is bad. In the worst case, we are going to end up with O of n runtime. It is slow in this really, really bad case where we just pick the items and they're connected in this really long chain. But it does seem like it's possible to improve on this, kind of. Because the main problem is if that tree ends up like really, really stringy. Is there any way we can maybe like reduce that stringiness? Like if we could get this tree to be more like compact, then it'll be much faster. Yeah.
So if you're connecting like nodes A and B, when you like first just get like the root node of A, and then for B, instead of what we're doing now, which is traversing recursively to get through to B, just when you're doing your recursive traversal through B, just set the root of every node there. So for example, if you have B, set its parent to, well, first get what's B's
interesting.
And then set its parent to the root of A. And then for whatever B's parent is, get its parent, set B's parent to the root of A, and then just repeat the same thing with B's previous parent's parent.
Okay. That is an interesting idea. I'm not going to say it on Zoom because that is spoiling, I think, 2 sections from now. But I will note that this still doesn't help the case where like every single time we accidentally like connect roots together, and because we never actually move up anything up. Yeah, it's unlikely, but it is possible that that happens. So you still get the same worst case runtime. Yeah. Interesting. Maybe we have some kind of order on the trees. Yeah. In effect, we kind of chose arbitrarily which one is going to be the parent. If we choose that more cleverly, then maybe we can get trees that are guaranteed to be flat. So let's take a look at this. Imagine that we're trying to connect this tree that contains 2 with this tree that contains 5. We have 2 options here. We can connect 3 as a child of 0, or you can connect 0 as a child of 3. Both of these yield valid tree structures. Which one do you think is better? How many people prefer the top approach? How many people prefer the bottom approach? Why do people prefer the top approach first? Yeah.
It has the longest like branch is only 2, whereas on the bottom the longest branch is 3.
Yeah. If we look here, this top one, it has the longest path of length 2, whereas this bottom one has the longest path of length 3. You go down 3, 0, 1, 2 here, whereas here the most you can do is 0, 1, 2. So intuitively, it seems like if we can choose this approach at each step, we're going to get trees that are shorter on average. So what do you think our rule should be to decide which tree to put on which? I heard something over there. Yeah, shorter. What do you mean by shorter? Yeah, less length. So in this case here, the reason why this happened is because this thing had a height of 2 and this thing had a height of 1. If we put the height of 2 thing under the height of 1 thing, then we're going to get a height of 3 total. But if we put the height of 1 thing under the height of 2 thing, then we're going to still get a height of 2 total. So we are going to prefer this. And it seems like if we always put the item with smaller height under the thing with bigger height, then we're going to end up minimizing the total height of the tree. Yeah.
Well, actually, never mind. That's
All right. So if we have a tie, we kind of have to break a tie arbitrarily. It doesn't really matter how we do that. But as it turns out, tracking the tree height is a bit annoying. It does work. It is going to get us the same results as what we're going to look into. It's just not going to work well with an optimization we'll look into right now. So what instead we're going to do is we're actually going to track in terms of the weight, kind of the total number of elements in that tree. So in this case here, this left side tree that has 4 items, this right side tree has 2 items. We'll put the 2-item tree under the 4-item tree. As it turns out, we'll be able to show that this ends up getting the exact same results. We'll get the same asymptotic growth as if we were only picking according to height. So as it turns out, we'll end up preferring that. So let's just do a quick example here. Which items goes to which in this case? What number changes in this backing array if we're following this process, where this item with the smaller weight gets put as a child of the item with the larger weight? How many people say it's A, that parent 3, this item here, gets changed if we try to connect 3 and 8? How many people say it's B, that item 0 gets changed? C, item 8 gets changed? How about D, item 6 gets changed? All right, seems like kind of consensus is item 6. Why is that the case? Yeah. Yeah. When we connect, we first find the roots. We have to do that regardless. So we go from 3 to 0, and we go from 8 to 6. And then we look at how many items the 0 tree has. How many items does your 0 tree have? 6. How many does the 6 tree have? 4. Which one's smaller? 4. 4 is smaller than 6, so the 6 tree gets put under the 0 tree. We prefer to connect it this way, and the way you do this is by just setting the value at 6 to point to 0. We don't really need much changes in the code. One minor detail that we need to worry about is now we need to check, where we need to keep track of the size of each array, or each tree. But the common way we do that is we kind of store that in the root node. So in this case, I'm using -4 here to represent the fact that this 6 tree contains a tree with exactly 4 elements in it. There are other approaches. You can create a separate size array if you want, and just look at the items size value. For example, here, 6 yields a size of 4, 0 yields a size of 2. Either way is perfectly valid. I think in the way that we're doing it normally is we're going to be doing this top approach where we just use the weight to be negative. We have a disjoint sets lab, which we canceled, but it is optional. It is available for you to try out if you want to try and write this code yourself. But we didn't see it as too necessary here, and we skipped it this semester. Yeah. So I claim that this is fast efficiently. Let's prove that is true. Let's look at kind of this worst case where we're trying to make trees that grow as tall as possible. First off, what is the smallest tree that we can have that has a height of 1? How many items do we need? At least 2? Why? Yeah, we just need to connect 2 items together. Regardless of which one we connect to which one, we're going to end up with a height of 1. Here we're using height to refer to the number of like connections. So just the node by itself has a height of 0. A node with a child has a height of 1. And no matter whether we put 0 or 1 and 0, we're going to have a height of 1. How do we get a tree of height 2 in this scenario? What's the smallest tree of height 2 that we can possibly create? 4? Why? Yeah, the only way we can create a tree of height 2 is if we try to connect a tree of height 1 with another tree of height 1. Because if we connect the trees of heights 1 together, then we're going to end up forming a tree of height 2. The smallest tree of height 1 has 2 items. The smallest tree of size 1 has 2 items. So the smallest tree of size 2 is if we take these 2 smallest trees of height 1 and then connect one to the other. What's the smallest tree of height 3? Anyone have a suggestion? You? Yeah, in the back. Why can't we connect something to 1? Well, because if we try to connect, for example, 2 to 1, then we're going to move up to 0 because we always find the root of the tree. And we'll connect 2 to 0 instead of 2 to 1. Is that clear? Yeah. So in order to make a tree of height 3, the smallest we can manage is we take a tree of height 2, we take a second tree of height 2, and we got to connect them together. So here's kind of what we have. We have these 2 trees of height 2. These are the smallest possible trees of height 2 we could possibly have. And if we connect these 2 together, then we're going to now get a tree of height 3. That's the smallest tree of height 3 we could possibly get. If we keep at this, what's the worst case height of this tree in terms of the number of items? Let's take a minute to discuss.
Yeah.
All right, let's bring everyone back. How many people say that the worst case height of this is constant, beta 1? Log n? Beta n? N squared. All right, for those of you who said log n, why is that the case? Seems like that's a consensus here. Yeah. Yeah. In effect, each time we increase the height by 1, we need double the number of elements as the previous height. And that's kind of the definition of log. Every time we double the size of the input, we increment the value of some function by 1. Yeah. Why do we add the 5? Because in order to make a 4, 6, 7 thing here, we needed to add 4 items. If we just tried to do 4, 6, and 7, then 7 would connect to 4 directly. Because we go up the list to, from 6 to 4. And we connect the 4 to 6. Yeah. You can talk after class and we can discuss further. Yeah.
Just assign, like, you know, a group have like 3 nodes. Like, why can't we have this assign 7 to have a paired on instead of assigning it to the paired on 6?
Why can't we assign 7 to 4? We could have, but we're kind of looking at this worst case scenario where we're always connecting roots to each other. Yeah, in this case, we never even noticed that 7 was connected to 6 because we only connected 4 and 6 together. Yeah, if we did try to connect 4 and 7 together, then that would make everything connected to 4, and that would be better. But we're looking at worst case in this case. But in any case, the worst case height of this tree is theta log n, which is really good. In effect, that's the worst case runtime because we need to go up this tree to find each item. And if the maximum height is log n, then that means that both of our connect and is connected operations are log n speed. Log n is really, really good. It is practically perfect for pretty much any cases. You can basically do a billion items and it will take at most 30 steps to get log n. Now, we did say we didn't want to use height. Why not? As it turns out, the worst case height for a heighted quick union is exactly the same. It's log n as well. There's actually another interesting point, which is that while using the height as the metric, it will minimize the worst case step of the node. Using the weight actually minimizes the average weight of a node, the average depth of a node. The math behind that is a bit trickier. Talk to me after class if you want to go behind it. But as it turns out, if you use weight, you end up with a better average runtime. And it also works better with the optimization that we'll be doing soon. Yeah. Weight is kind of the total number of items in the tree. So the weight of this left side tree is 6 because there are 6 items. The weight of this right side tree is 4 because there are 4 items. Yeah. So we are successful. We managed to get log n runtime with our weighted quick union. It's really good. Basically, if you look at 10 to the 9, that's the difference between 30 years of work, 1 item per second, and 6 seconds of work. Which is better? 6 seconds, right? This is a massive difference. And basically, at this point, it works perfectly fine. You can use your weighted quick union. It is going to work for pretty much any data set that you're working on. Can we do better? Let's do better. This is kind of what you're talking about. And the idea is, since we're already traversing up this tree, we find a lot of items that we know for a fact are connected to that root. So let's just connect those things to the root directly as we do this. When we go up from 15 to 10, we'll look at 11, 5, 1, and 3 and find that their roots are all 10. So what we're going to do is we're just going to connect them directly to the root immediately as we do this. Does this add additional runtime? How many people say this doesn't add additional runtime? How many people say it does add additional runtime? It does add additional runtime. That is true. But it adds only a constant amount of additional runtime. We're already going up this path anyway, so that takes log n time. And connecting log n items to the root, that also takes log n time. So total, we don't actually change the growth of the runtime. Everything still stays log n in this worst case. And as it turns out, this reduces the total amount of work we need to do for future calls. Now, when we next call 15, we see the root immediately at 0, instead of having to go back up 11, 5, 1 a second time. So let's just do a quick check. What happens after we connect 14 and 13 together? Which items get changed? Anyone want to suggest? Yeah.
6, 8, 13, 14.
Yeah. When we call this, we'll look at these paths and we'll find all the items that are connected to 0. We'll connect the 6, the 8, the 13, and the 14 up to 0 because they are not directly connected to the 0. But we found that their root was 0, so we might as well mention that on our array. Once we do that, our tree is now really, really short. So many items are connected to 0, chances are we'll end up with one of those items. By compressing this tree, we're going to keep this tree nice and short. And as the number of nodes grows, we're going to end up getting larger and larger trees in the worst case. But generally speaking, each time we do an operation, our tree is going to end up getting shorter. After enough operations, our tree are going to shrink all the way down to height 1. Everything is going to be connected directly to the root. And at that point, everything is fast. Now, it is still possible to get a log n height tree. That's if you only ever call these on the roots. Because if you call on the roots, then we don't find new items to connect to new roots. But if you do a root connect, that's already theta one time. And at each time we do one of the slow log n operation runtimes, we shorten the tree by a lot. So because of that, if we look at the average runtime over a large number of operations, the amortized runtime, we're going to end up getting a better runtime than theta log n. What's that runtime? As it turns out, in 170, you'll show that this is O of log star of n. Log n is kind of the number of times you need to divide a number by 2 to get down to 1. Log star is the number of times you need to call the log operator to get down to 1. And it is really, really slow to grow. Log star of n, if you send in 1, you get 0. If you send in 2, you get 1. 4, you get 2. 16, you get 3. In order to get up to 4, you need 65,536 items. In order to get to 5, you need 2 to the power 65,536 items. In comparison, there are about 2 to the 40 or so atoms in the universe, I believe. Somewhere between 2 to the 40, 2 to the 60-ish. I don't remember the exact number, but it's not much. In comparison to this, you're not getting anywhere close. Sorry, did I say 2? I mean 10 to. 10 to the power 50-ish, right?
I looked it up. It's 80. But...
10 to the 80. Okay. 10 to the 80 is 2 to the 200 or so. It's nowhere near. In fact, you can prove even better. The average runtime is Ackermann of n, and the Ackermann function is this thing. If you call subtraction 1, division 2, logarithm 3, repeated logarithm 4, repeated log star 5, then that is inverse Ackermann of n. To get to an inverse Ackermann n of 5, you need 2 to the 2 to the 2 to the 2, 65,536 times. For all intents and purposes, this is basically constant. So overall, our data structure is perfect. We get constant time effectively.
Email composition. Yes.